got this beam with a pivot point in the middle, and I've got two 1 Newton forces. They're both at the 2 marker on this beam. There's different holes in here, and they've all got numbers. So they're both at 2 marker. I've got 1 Newton force both sides, and you can see that it's balanced. It's not going anywhere. It's in what we call equilibrium. So if I were to change this setup though, and I'm going to move this 1 Newton force, I'm actually going to move it in a little bit to the 1 marker. It's now not going to be balanced. It's now going to have an overall turning force, which is going to turn the beam. And if I were to say to you though, right, I've got the 1 Newton at the 2 markers. If I'm going to move it to the 1, how much weight do I need to put here in order for it to be balanced? So I've got 1 Newton here, but it's twice as far away. So if we think about that, I'm going to need to have 2 Newtons on this side. Right, and hopefully you can kind of follow that logic, and it does now balance. It's not quite perfect, but that's because of the equipment, not because of the physics. So I've got 2 Newtons and a distance of 1, and I've got 1 Newton and a distance of 2, and it balances. And that the way that we can calculate some of these turning forces is by calculating what's called a moment, which is a force times by the distance. And what we've done logically here is we've said that the clockwise moment from this weight is that turning force has to be equal to the turning force, the moment from this weight, the anti-clockwise moment. And with that, we can work out the weight of some mystery objects, or we can maybe work out some distances. How far do I need to put something in order for it to balance, and solve problems to do with moments. I've got this mug here, and I'm going to try and weigh this mug using this equipment. So put this on here. I have done a little bit of trial and error earlier, so I know that this is going to work. The mug is on the 5 marker, and I've got 2 Newtons on the 8 marker. All right, so we're going to use what's called the principle of moments. At this clockwise moment has got to be equal to this anti-clockwise moment from the mug to calculate the weight of the mug. And then I'm going to see if I'm right. Okay, so whenever we start this, I always like to start by writing that the clockwise moments equal the anti-clockwise moments. And that's called the principle of moments. So we've got our the clockwise moment here was the 2 Newtons multiplied by the 8. It doesn't matter that this distance is not in meters, it's in arbitrary units, but I'm going to do the same unit system on the other side, so it actually doesn't matter. Also with this, although a moment is force times distance, it doesn't matter really if I use mass here. I could use kilograms or grams, because I'm going to use kilograms or grams this side as well, so it will just cancel out. But anyway, so there's force times the distance, and then I've got the force of the mug, which I'm going to call W, maybe W subscript M, so that when I get more complicated problems, I know which my unknowns are, multiplied by that distance as well, which was 5. It was 5 away from the pivot point. So then I'll end up with 16 equals, I'm going to call it 5 Wm, and that means that the weight of the mug will be 16 over 5, which is 3.2 newtons. So hopefully the mug weighs 3.2 newtons. Okay, let's see if we were right. It's not just the mug, of course, it's actually the mug and the hook. So 3.2 newtons is 320 grams. And you can see here, look, I've got 0.3264 kilograms. So this is actually pretty much bang on. Of course, that would round to, if I convert that into newtons and round it around 3.3, but still, I'm pretty happy with that I've managed to weigh the mug and the hook as well by balancing it on the ruler.